Hi everyone, this is Nexus of Thought. This is a video for my students on special relativity. So the key ideas with special relativity that one needs to appreciate is the fact that the laws of physics are true for all frames of reference. And because the laws of physics are true for all frames of reference, what that ultimately implies is that the speed of light, since it's not dependent on an ether or something along those lines, is always measured as c across all frames of reference. So that is 3 times 10 to the 8 meters per second. Now, if every frame of reference is measuring c as that particular value, in a vacuum, of course, then that means that former absolutes, such as space and time, have to give to actually accommodate this. And this is what is critical about the speed, about special relativity. Because we used to believe that both time and space are absolute. Everyone measures them the same. And this is how the world looked like in the Galilean and the Newtonian framework. Now it turns out, because the speed of light is actually fixed across all frame of reference, we have to bend something else, and that leads to a direct impact in time and space. So this follows from the first postulate. The other idea, which is very, very important in special relativity, is that it is impossible to actually design an experiment to tell whether an object is at rest or traveling at uniform velocity. You cannot do this. So the situation of being at rest and uniform velocity from a physics standpoint is actually treated as the same. And this, of course, has implications in special relativity. Now, what actually happens as a result of these two postulates and the fact that the speed of light itself is an absolute, but time and space are not, and that we cannot tell the difference between constant velocity and at rest, what follows from all of this is huge changes in certain paradigms. The first is the notion of time dilation. And what actually happens in time dilation is two observers in different frames of reference will have a different understanding of how much time has followed between a specific event. You have the individual who measures proper time. This is the individual who sees an event occurring at the same position in space. And then you have the other individual who measures what we call relativistic time or measured time. And this is the individual who sees an event occurring at different positions in space. And what actually happens here is that the individual who experiences relativistic time actually experiences what we call time dilation. They will have a greater measurement of the time elapsed for between two events than the person who's at rest relative to those two events. Now, of course, you can develop the relationship by careful use of Einstein's reasoning, but also by careful use of Pythagoras. And you can show that the relativistic time, delta Tm, will always be greater than or equal to the proper time, which is delta Ts. So the individual who sees the event occur at two different places in space actually measures a larger time. And the discrepancy between your delta Tm and your proper time becomes even larger as the for an object that's traveling at a very, very high speed v. So as v approaches the speed of light c, then the discrepancy between these two measurements of time become even larger. In fact, it actually tends towards infinity. And we can measure that discrepancy for those two by looking at what's called the Lorentz factor or the gamma factor. That actually tells us, based on the ratio of your velocity to that of the speed of light, what the discrepancy is going to be in the two times. And it ramps up in a hyperbolic fashion. So time dilation is in fact actually what occurs. And a lot of people think that this is actually something that is not real. It's actually an imagination, but it actually does occur. We have seen this with atomic clocks that we've synchronized to several decimal places of accuracy. And then when we placed one on a plane and one on Earth, and when we aligned them back on Earth after the one on the plane had gone around for a while, we see that there is a discrepancy in the time that's measured by the two atomic clocks that can be explained by the time dilation equation. We've also noticed that fast-moving muons or various other subatomic particles, the half-life for those particles is different to what we would measure if it was at rest relative to the laboratory. And this is again in accordance with the time dilation equation. So this is very, very big, because in Galileo, as I said, everyone agreed on time. It was one thing that we all said was we measure the same time, we'll measure different velocities, but we all agree on the same time. In Einstein's special theory of relativity, the discrepancy occurs around around time. Different individuals, based on their reference frame, will measure a different time between this period of between two events. And this is a consequence of the rigidity of holding the speed of light constant for all frames of reference. Now, the other factor which is also changes because of this is space, particularly length. And what we notice from special relativity is that if an object is moving relative to a length being measured, then that individual that's moving relative to that length will actually measure a shorter length than an individual who's at rest relative to that length being measured. And of course, this is called length contraction. And the discrepancy between the length measured by the person who's at rest relative to what's being measured, which is basically your proper length, the discrepancy between the two is consistent with the same gamma factor that we talked about in time dilation. So both time dilation and length contraction, an impact on time and space, are actually a function of special relativity. Now, they are not the only functions of special relativity. What we'll see as well is that relativistic momentum, we have to change the momentum equation from the classic version. We have to put in the gamma Lorentz version, because what actually happens is that there is an increase in the apparent mass of the object, which we can infer from its actions in collisions, infer from its momentum. So momentum also changes from the classical version, and that is consistent with gamma. And this also impacts kinetic energy as well. So there are a number of factors that are forced to radically alter as a result of the two postulates of special relativity, particularly the fact that the speed of light is constant across all frames of reference, and that one cannot design an experiment to distinguish between at rest and constant velocity. Because of these two, we are forced to change our understanding of constant time. It's no longer constant or absolute. We don't no longer have absolute length or absolute space. We also have to rechange our understanding of momentum, kinetic energy, and ultimately total energy. And from all of this, actually, it comes the development of Einstein's mass energy equivalency. So special relativity is an incredibly important change in the way we think about the reality in the world of kinematics, as well as our understanding eventually into things like electromagnetism and the speed of light. If you find this video quite useful, please give it a thumbs up and keep well till next time.